What's up, everybody? I'm Sid, and today I'm going to talk to you about cipher block chaining, or CBC, and an attack against it called the padding oracle attack. I hope this is a good reference for you all as you're coding up your solutions for part 2.3 of the project. I'll be going into the scenario for the padding oracle attack, as well as the logic behind the attack itself. To talk about the scenario, let's imagine that we have a server that takes variable length messages from all sorts of clients. It wants to enforce two key security principles. One, confidentiality. Any messages sent to it can only be read or understood by the intended sender and intended recipient. Two, it wants to provide integrity, stating that any changes to the messages in transit can be detected. And the way it's going to provide both of these two key principles is by one, enforcing that plain text messages must be encrypted before they're sent to the server, and two, the sender must include a message authenticity code, or MAC, of the plain text message as well in order to provide integrity. You can think of this as the output of a hash function such as MD5 or SHA-256. Now we're going to look a little bit deeper into CBC encryption. Like I mentioned earlier, CBC encrypts messages or variable length messages, and because of that it uses a block size format similar to how MD5 hashes messages. For this example, we're going to assume a block size of 4 bytes. So for a 12 byte long message, up top over here are plain text, it's going to be split up into 3 blocks. And on the bottom over here, we have our ciphertext. And similarly, we're going to have a 12 byte ciphertext that's outputted from the encryption scheme. Let's first look at block number 2 to understand what's going on. Then we'll learn a little bit more about the initialization vector. Looking at block 2, we have our 4 bytes, P5, P6, P7, P8 of plain text. They're first going to be XORed, bitwise XORed, with our ciphertext from the previous block. So block 1's output is XORed with the plain text of block 2, then it's fed through the encryption algorithm. This is where the chaining part of CBC comes from, right? And after it goes through the encryption algorithm, it outputs block number 2, and block number 2 is then fed XORed with the next plain text block before it's encrypted. And you can imagine if we had a longer message, it chains similar to that. Now, since for block number 1, there is no ciphertext block before it, we actually generate a random string of bits known as an initialization vector. This is the same size as the block size, and this is XORed with the plain text of the first block before it's fed through the encryption algorithm. So you can think of this as a seed for the CBC encryption algorithm. I've also included a XOR recap in case any of you may have forgotten since 203. Anything XORed with itself is 0. Anything XORed with 0 is itself. And I've also included a small example. This is the binary representation of the lowercase letter a in ASCII, and this is the binary representation of the lowercase letter z in ASCII. And if they're XORed together, this was what the output would be. Now, before I go into decryption, there's one crucial thing left to mention, and that's padding. Since CBC encrypts and decrypts messages in this fixed length block size, we are going to have to pad messages that aren't a multiple of the block size to the correct length, right? So here's the CBC padding scheme. Using our block size example of 4 bytes, let's say that we had a message that was 7 bytes long. We are going to have 1 byte of padding at the end of it, and that 1 byte of padding will have the value of 1. For a 6 byte long message, we are going to have 2 bytes of padding, and each of those bytes are going to be of the value 2. With a 5 byte long message, we are going to have 3 bytes of padding, each of those of the value 3. And I'm going to use the hexadecimal notation to represent these values. So 0x3 represents the value of 3, which is written in binary right over here. Now, for a message that is the correct, or is a multiple of the block size, we are actually going to attach onto it a whole another block of just padding. So any message you send that's been encrypted using CBC will always have padding attached. Now let's take a look at CBC decryption. As we can see, CBC decryption looks extremely similar to CBC encryption it's just its inverse. Looking at this second cipher block, first the cipher block is passed through the decryption algorithm, then it's being XORed, bitwise XORed, with the previous cipher block, or cipher block 1 in this case, before receiving the plain text of block 2. And a similar thing is happening with cipher block 3, and if this message is longer, so on and so on. Looking at our edge case with the first cipher block, since there's no previous cipher block before it, we are going to XOR the decrypted version of this cipher block with the same initialization vector that we use to encrypt these messages in order to receive plain text block 1. Now, before we go into the actual attack, it's crucial to talk about what the server is going to do when it receives these messages. I talked about in the beginning of this video how the server wants to enforce two things. 1, confidentiality, and 2, integrity. Since the sender is going to send over a MAC of the plain text and an encrypted version of the plain text, the server is going to have to first decrypt the encrypted text into the plain text, and then use that plain text in order to check the MAC. So the server is going to have to check the encryption first before checking the MAC. From the sender's perspective, this is called MAC then encrypt. So if you think about the sender is going to first take this message, the plain text message it wants to send, create a MAC of this message, then encrypt this message, right? This would be different from encrypt then MAC, where the sender would first encrypt the plain text message, then using that encrypted plain text message, create a MAC of that. So looking at what the server is going to do, since the server needs the plain text in order to check the MAC, it's going to first check the padding of the encrypted message, right? Since if the padding is incorrect for this message, chances are this message hasn't been encrypted properly and it's a garbage message it received, right? But if the padding is correct for the message, doesn't matter what the plain text is, it's going to then check the MAC of the message. So if the padding is incorrect, the server is going to return a padding error specifically. And after decrypting the message and checking the MAC, if the MAC of the plain text doesn't match the MAC it received, then it's going to return a MAC error. And it's crucial to mention that the server can return 2 possible error messages. First, a padding error, or second, a MAC error. And the user is going to know which one it is. This is where the term padding oracle in padding oracle attack comes from, and is a crucial detail in order to make this attack actually possible. Now for the attack, let's assume an attacker, Mallory, intercepted a 12-byte long message and its associated MAC. Let's also assume that Mallory has access to this padding oracle server, and she can submit any number of messages to the server, and she'll receive a response back from it, saying whether it's a valid message, whether there was a padding error, or a MAC error. So I left up the decryption diagram from before in order to explain this attack, and let's assume that the C1 through C12 message is the one that Mallory intercepted. So the gist of the actual attack is that Mallory is going to submit a slightly altered version of the ciphertext she intercepted, and depending on the error she receives, a MAC error or a padding error, she's going to incrementally, byte by byte, decrypt the whole ciphertext. For example, we're using a 4-byte block, right? So each of these 1 cells is 1 byte. 1 byte is 8 bits and has 256 possible values, right? So let's look at this specific byte right over here, C8. So this is the last byte of the second to last block, specifically. With this byte, this could obviously have 256 possible values. Let's say Mallory just incremented this from the original ciphertext she intercepted, this value C8 just by 1. And she submits that to the server. What exactly is going to happen? First, the server is going to decrypt this ciphertext she received, this altered ciphertext. Obviously, P8 is going to be different, right? Since C of 8 is changed when it goes through the decryption algorithm and is XORed with the byte block before it, P8 obviously will be different, but also P12 will be different, right? Since when C12 gets decrypted, it gets XORed specifically with byte C8, in this place. Chances are this P12 is going to turn into some completely random number. So let's just assume for this case that for this new value of C prime of 8 that we submitted, we are going to get a new P prime of 12 of 0xAB, just something completely random. What will the server do? The server expects padding, right? I talked about padding earlier, and the server expects some sort of padding at the end of every single message that it receives. Since it sees the 0xAB and it checks the next byte after it it's going to see 0xAB and it's going to see that it doesn't match any padding scheme it was expecting, so it's going to return back a padding error. Now let's say that Mallory instead submits 256 altered ciphertext with every single possible value in C8. So the whole ciphertext remains the same, every single byte, but she submits it with a different value of C8 every single time. You can imagine we are going to get every single possible value of P12. And for most of those, we are going to receive a padding error, right? Since we're going to get something completely random like 0xAB in this spot P12. But for one specific case, Mallory will actually receive back a MAC error. And let's look at that specific case. So when she submits a new C prime of 8, some random value, and P prime of 12 shows up as 0x01, the server is going to see the 0x01 when it's decrypting this message, and it's going to interpret that as valid padding, correct? Then after she decrypts the rest of the message and she checks the MAC, obviously the MAC won't match since the ciphertext was changed, right? But Mallory's going to receive back a MAC error instead of a padding error. And this is key to decrypting this final block P12. So let's define C prime of 8. Let's say that C prime of 8 is this one special value that she puts in the spot C8 where she receives back a MAC error instead of a pad error. I'm just going to write this right here. So C prime of 8 is the case where she receives a MAC error. Let's also define one more intermediate variable, D. So each of these cipher blocks, they're each going to go through the decryption algorithm before they're XORed with the block before it, except in the first block's case where we're XORing it with the initialization vector. And let's call that D. So for C9 through C12, after it goes through the decryption algorithm, but before it's XORed with the ciphertext of the block before it, let's call that D9 through D12, right? So we can write this this equation right here, that P12 is equal to D12 XORed with C8, right? And then we could simply just rearrange this equation to say that D12 is equal to P12 XORed with C8. Now in this special case where she submits this special C prime of 8, we know that we get a new special P prime of 12 that equals 0x01. And we also know from this equation right here that P prime of 12 is equal to D12 XORed with C prime of 8. And keep in mind, this D12 is not D prime of 12. She did not change C12 at all. She only changed C of 8, right? So when C12 goes through the decryption algorithm, it's the same as before. So we can say that P prime of 12, which is equal to 0x01, and then we can say that P prime of 12 is equal to D12 XORed with the special C prime of 8. Now let's simply just substitute out this D12 for this equation right here. I'm just going to write this up here. So this equation holds true as well. Now, this P12 is the original P12 of the decrypted message. And we know these other three values. Mallory intercepted the original message, right? So she has access to the old C8 that she intercepted originally. So she has this P She knows P prime of 12 is equal to 0x01, which I'll replace in right now. Right? And she knows C of 8, the original C8, and she knows her guess C prime of 8 that resulted in this MAC error. So we can just rearrange this to figure out what the original P12 or decrypted last byte of the message is. So using this equation right here, for the one time that she got the MAC error, she's now able to figure out what P12 originally was. This is simply just because the server returned back a MAC error instead of a padding error. A potential question you may have now is, given this method of decrypting the last byte of the last block of the ciphertext, how can you extend this method now in order to decrypt the whole last block and eventually the whole message, right? But before I go into that, I want to cover one crucial detail, is that now knowing the value of P12, we can now calculate the value to put in C8 spot to get any value we want to show up in P12 spot, instead of just having to randomly change the value of C8. And so I'll show you the math behind that. Let's define this new special value that we want to put into C8 spot to get whatever value we want to show up in P12 as C double prime of 8. We're going to calculate C double prime of 8 to be equal to the original C8 XORed with what we now know is P12 and XOR that with our new guess. This guess being any value that we want. In this example, I'm just using 0x02. So we can calculate a new C double prime of 8, and this C double prime of 8 will guarantee that 0x02 will show up in P12 spot. So we can define P double prime of 12 as C double prime of 8 XORed with D12. This is based off of these two equations and what we've defined as D12 or D in general, right? So we can do a simple substitution. P double prime of 12 is equal to C8 XORed with P12 XORed with our guess 0x0, or not our guess, but the value we want to show up in P12 spot, 0x02, XORed by C8 and P12. And we know that this P12 and this P12 will cancel, this C8 and this C8 will cancel, and we will get a new P12 of 0x02. How can we now decrypt P11, the next byte after P12? Let's assume the attacker Mallory permanently changes C8 to this new special value C double prime of 8, where P12 will always decrypt, or C12 will always decrypt to this value 0x02. When she sends this new altered ciphertext to the server, she knows that the first thing the server is going to do is check the padding. And when the server sees this 0x02, the server is going to think, okay, I need to check the byte right next to it to see if that's also valued at 0x02. If it is 0x02, then I know this message has valid padding and I'll check the MAC, right? Assuming that she did not change C7 in any way, chances are C7 is some random value, let's say 0xAB. The server is going to see this 0xAB in this next spot and think this message doesn't have valid padding, I'm going to return back a padding error. Now, Mallory can similarly figure out C or P11 in the same way she figured out P12. What she's going to do is keep the special value of C double prime of 8 and repeatedly change C7 to every possible value, all 256 of them, until she receives a MAC error instead of a padding error. For most cases, when she changes C7, she's going to receive some different value is going to show up in P11 spot, but it still won't be valid padding. When 0x02 shows up in P11 spot, the server is going to see 2 bytes valued at 2, which is valid padding for a length of 2, and return back a MAC error instead of a padding error. And using this new special guess that she had for C'7 that gave us this MAC error, she can figure out what P11 is. This is the exact same math that I did for P12, but I'll write it out for you once more. So let's say C prime of 7 is the case where we got the MAC error. We know when we submitted C prime of 7, we got a special P prime of 11 that equaled 0x02. We also know, based off of P prime of 11, can be rewritten in terms of our intermediate vector D, as well as in terms of C7. Keep in mind once more, this is still D11, not D prime of 11, since we've not changed C11 or C12 in any way. Now we're simply just going to replace D11 with what it represents in terms of the plain text and the original ciphertext. I'll also replace P prime of 11 with 0x02. Now we can just simply rewrite this to solve for P of 11. We know every single value on the right side of this equation, so we can now figure out what P11 is. Now that we know what P11 is, we can now change C7 in any way to get any byte that we want in P11 spot. So to solve for P10 now, we can simply change P12 and P11 to show up as 0x03 instead of 0x02, and then keep on changing C6 until we get a MAC error at P10 spot instead of a padding error, right? And then it's the same exact calculation all over again. The next question that comes up is, how will I extend this to the next block? Keep in mind, no message can have a padding greater than 1 block size. So we can't simply extend this to P8 by writing in 0x05, 0x05 in the whole last block and trying to get 0x05 to show up in P8 spot. What we can instead do is simply just not submit this last block. Once we've decrypted this third block, P9 through P12, we can simply act as if we have a 2 block long message instead of a 3 block long message. Assuming this block never existed, we can simply keep changing. We can start by changing C4 until we get 0x01 to show up in P8 spot and solve it in the exact same way. Hopefully this video was a great intro into the padding oracle attack and the scenario for how it works. This padding oracle attack is possible because of one, the way the server is checking messages, first checking the encryption, then checking the MAC. This is related to something called the cryptographic doom principle. And this attack is also possible because the server chooses to inform the user what type of error it returned. That's why it's the padding oracle. It returns either a padding error or a MAC error, or if it's a valid message. While the server is doing this explicitly in this example, by returning literally you have a padding error or a MAC error, the server could also do this implicitly. Maybe the server sends a padding error much quicker relative to when the message was sent than a MAC error. This could also be used as an indication of what type of error occurs.